Hello students, welcome to the IMS GATE Academy. First of all, please let me know how are you. Do it fast. Alright, so guys, please do share the session and please inform the student and your friend that the class is already started and definitely we're going to have a great session. Alright, so as you know that we had already completed the 4 lecture and this will be the lecture number 5, and in this we will going to study a lot of thing about the electrical machine, which is the requirement of the basics. Alright, so this is the lecture number 4 in which I will going to cover the types of EMF, force on conductor and the dot conversion, which is one of the important aspect of the transformer. Alright, so let us enter directly into the topic, and please guys do share the session and please like the session by hitting the like button, and also inform your friend to join as quickly as possible. And one more thing, if you have not yet subscribed the IMS GATE Academy channel, do subscribe that, and also press the notification button, or you can say the bell icon, so that whenever we are coming live you will go directly going to be notified instantly. All right, so and also if you want to opt any courses from the IMS GATE Academy, you can find the counseling what to say the free counseling, and you will going to get a phone number over there in over your screen, and you can contact. All right, whether you are from Ahmedabad, like anywhere, definitely you will find one of the number and you can contact, and definitely you will going to have a great what to say the great feeling once you're going to get the counsel from our backend team. All right, so let us start with the lecture, which is lecture number 5 over here. All right, so first we will see the Lorentz force, because this is the one of the most important criteria to get an idea about the motional EMF, or you can say the dynamically induced EMF. In the lecture, in the last lecture, basically the lecture number 4, we have discussed about the types of, means I have given you an overview on that. All right, so in that I told you we have two types of EMF. First one, dynamically induced EMF, and the second one, statically induced EMF. So statically induced EMF is the EMF where rotor, or you can say conductor, is not moving, means the conductor is static, and in that whenever the EMF is inducing is known as statically induced EMF. And in the second part, whenever the rotor or a conductor is moving and EMF is going to be induced in that, then those EMF or those kind of EMF is known as motional EMF or dynamically induced EMF. Done? So, the force on a moving charge first we will study, and force on a moving charge is what basically whenever a charge is placed under a magnetic field, this is a magnetic field, and a charge is moving in that magnetic field, then the moving charge experience a force. Am I clear? All right, just a second. Now let me make a charge over here. Suppose this is a magnetic field. This region is a magnetic field where magnetic field is inside to the board, or you can say inside of the plane of the paper for you. So since it is inside, so I have marked those magnetic field as cross. This kind of notation we have used in the last lecture, and why we have used to just simplify the diagram. All right, so we don't want to make the magnetic field over the region, just we want the initial of that the magnetic field. All right, so the cross implies that the magnetic field is moving away from me or away from you. So in the also in that case, for my means basically for me it is inside the board, and for you it will be inside the paper or page, you can say. Now let us take a charge which is Q. A charge which is Q. Just a second. A charge which is Q. Now, let me take this charge is moving. A charge is moving in this direction with a velocity V. Okay, and this is your magnetic field density. Magnetic field density. Done. Now, what Lorentz has said that whenever a charge is moving, then it will experience a force, and that force is given by F vector, which is equal to charge placed in a magnetic field, which gives the force as V, velocity of a conductor, into magnetic field density. This is one charge. Okay, so this is the this is one force. This is due to the magnetic field, plus one more force will going to be occur, and that is due to the electric field. So Q into E. These are the things that we have studied, or you will going to study in the you are going to study in the EMF. Done. So basically, this is what? This is force due to magnetic field, or simply let me write force due to magnetic field plus force due to electric field. Done. So this is the Lorentz law. So please keep this thing in mind. This is very important law, and whenever you are going to study in the EMF, you will going to see all those things in detail. All right. So see, the next topic is force on a conductor carrying a current in a same direction. We have seen that whenever you are going to have the current, and the current is flowing in the magnetic and the current is basically the conductor. A conductor is moving in a magnetic field, then it will experience a force, and that I will going to derive in a bit. So see here. Let me derive here so that we can have some space for the next topic. Okay. All right. Now see here, I will going to derive an expression for the force when a current is flowing in the conductor and the conductor is moving in the when a current is in the magnetic field, and that conductor will experience a force. How it will going to experience? See, F magnetic field is given by Q vector, not Q vector, Q times V cross B. What is V? V is the velocity, B is the magnetic field density, and Q is the charge. Now, this velocity is basically what? This velocity is the velocity of the charge, or you can say the velocity of the electron. So the velocity can be happen in two manner. First velocity is known as drift velocity, and the second velocity is known as diffusion velocity. So drift velocity is always occur in the presence of your electric field, whereas the diffusion velocity is under the presence of a source, or you can say a source voltage. So basically, this V is the drift velocity. Let me write Vd into B. Okay. Now I can replace this Vd with change in displacement by time. So this is the displacement dl vector divided by dt into b vector. Now let me take this dt to the q. Okay, one more thing. This is the force equation. Then for small or you can say for a small amount of charge, what will be the force? Del F, isn't it? That will be del F. So it will be del Q for the means the force experienced by small charge. Now let me take dt to here. Dt to here. Just a second. This implies dq or df magnetic field, this is equal to dq by dt. L is the length of conductor into magnetic field strength. Done. So what is dq by dt? This is current. Di dl into b vector. So this is the force. This is the force which will going to be experienced by such a small amount of current. But if you take the integration or due to whole charge or due to the complete charge, what will be the force? Just integrate it. You will going to have the force under the presence of magnetic field as I dl vector cross b vector. So this is the magnetic force equation whenever a charge is placed under the magnetic field. So these two are same. These two are same. One's give the information related to the charge and other will give the information about the current. Alright, so basically both are same. This is basically what? A charge moving inside the conductor, whereas this is the current carrying conductor placed under the magnetic field will experience a force. Done. Alright, so let us move to the force on a conductor carrying a current in same direction. So here I will going to take a two conductor and means two separate conductor, and in that separate conductor first I will take the case where the current is flowing in the same direction. Alright. So let me take a first case here. Okay, just a second, let me draw it. Okay, so this is the conductor. I am not showing a complete here. Alright, so a conductor is basically what? It is having some length, na? So I am showing here a small portion of that. Means the if you are seeing the conductor from the cross sectional area, it will be circular. So this is the two separate conductor in which the first current, let us take here I1. This is the first conductor where current inside that is I1, and this is the second conductor which is having the current I2. Alright, so the current here is what? Dot. Dot means it is coming out from the board or coming out from the plane of paper. So this means that it will be visible as a, what to say? It will be visible as a dot, isn't it? Now see, this conductor which is carrying a current, it will give you a magnetic field, isn't it? We have seen in the Fleming right hand palm rule. So here the current is coming outward. So the forefinger, sorry, this forefinger will curve in such a direction that it will going to produce a magnetic field. So here it will going to give the magnetic field in this direction for conductor 1. See how it will going to give outside anti-clockwise. Okay, this is the magnetic field which is flowing in the anti-clockwise direction. So this is magnetic field due to current I1. So B1, B1, and here what will be the direction of the magnetic field? B1 here as well. Done. All right. Now let us mark the magnetic field for the I2. Similarly, it will going to have the direction in what to say in the anti-clockwise. See for I2. So let me copy this. Okay, so here the direction for magnetic field is in anti-clockwise, which is B2. This is B2. Done? All right, now let us find the force. Okay, wait a second, I need to remove this one. Let us find the force why this is not going. Wait a second. All right, now let us find a force experienced by a conductor. Let us find a force experienced by a conductor 2. Conductor 2, let me write here. This is conductor 2 and this is conductor 1. Okay, so force experienced by a conductor which is equal to F12. So force of conductor 1 on conductor 2 means F12. Now see, this is equal to current of the second conductor, so which is IDL. Please remember the formula IDL cross B. So current element of the second conductor, which is I2 DL2, means the length of the conductor 2 into magnetic field density, or the or you can say the magnetic field density of the conductor 1, which is B1 here. All right. So the B1, so this magnetic field B1 exerts a force on this conductor too. All right. One more thing. This is the magnetic field strength. Here B1 is what basically equal to, this is equal to mu naught H. This is mu naught H, and here B1, so we need to take H1. And what is H1? This we have seen in the EMF, in the magnetic field, or you can say in the magnetic field density. This H1 is magnetic field strength, and this is given by I1, current of I1 divided by 4 pi A. So this is the magnetic field strength of C1 conductor, or you can say conductor 1. All right, just a second. Now, what is A here? A here is the distance between these two conductors. Okay, this distance is A. So I1 upon 4 pi A is the expression for the magnetic field strength. We are having like this here C1, and at point here I2, or you can say at the dot point, we are finding the magnetic field strength, and this is given by I1 upon 4 pi A, and this is in vector. This is vector. All right. Now let us remove the vector in terms of their magnitude and direction. So this I2 will be I2 only. This will become magnitude del L2. And what is the direction of L2? So for that, let me mark the XY plane axis. This is X axis, this is Y, and this is Z, and all are mutually perpendicular to each other. Done. Now see, this I1 current, okay, just a second. Yeah, this del L2, this del L2 will be what? Will be the length or the direction of the current which is having in the conductor 2. So this I2, or you can say I2 del L2 will be together, isn't it? I2 or I2 del L2 will be together. Since this I2 is coming outward, so it will be in the direction of X. It will be in the direction of X. Let me shift somewhat upside, just a second. Done. So this is what? This is having the direction as AX cap into times I1 upon 4 pi A. Now what is the direction of magnetic field, which is B1? B1 is here, and it is in AZ direction, isn't it? It is in AZ. See the magnetic field in this conductor due to current 1. So it is upward. So here it will be AZ cap. So can I write this value I2 I1 upon 4 pi A, and this is AX cross AZ. So AX cross AZ means what? AX, AY and AZ. In the yesterday class we have seen. So we are moving in the opposite direction. See, from AX to AY. So we will have to take the negative sign. So it becomes minus AY. So it becomes minus AY. And we forgot to write del I2. Okay, first let me write del I2. So del L2, and what is the direction that we have got? AX cross AZ cap. Wait a second. Okay. So AX cross AZ will be what? This is equal to F12 I1 I2 divided by 4 pi A times del L2 into AX cross AZ will be minus AY. So let me write directly here minus AY. Yeah. So minus AY will be what? In this direction. If AY is here, minus AY will be here. So force on this conductor, is in this direction. This is F12. F12. Now let us find the force on conductor 1 by the conductor 2. So it will be equal to, so F21. So force of 2 on conductor 1. So this is equal to I1 del L1 into, or let me write here, into C. If this is B1, so it will become B2. Alright, so this I1 del L1 and B2 is mu naught H2 I1 del L1, this is vector, into mu naught. For H2, the current will be I2. So I2 upon 4 pi A vector. Done. So this will become I1 and this is del L1. And what is the direction of del L1? Will be in the current direction. So it is outward, so AX. So this will be AX vector into mu naught I2 upon 4 pi A. And what is the direction here for the magnetic field? B2. B2 is downward. See here, in this conductor, the B2 direction is downward. So downward means minus AZ. Minus AZ vector. So this, okay, let me write here. I hope this is visible. Okay. So this is equal to I1 del L1 into mu naught I2 upon 4 pi A. So AX cross minus AZ. So can I take minus of AX cross AZ? This AX minus AZ will be written as minus of AX cross AZ. So AX cross AZ is what? Minus AY, and due to this negative sign, it will become plus AY. Alright. So plus AY means what? The force on this conductor will be in Y direction. So here the force will be in this direction. So this is F21. Now it is very clear that whenever a current is in same direction in a two conductor, whenever a current is in same direction, then the conductor will going to have the force of attraction. Therefore, let me write the conclusion here. Therefore, whenever a two conductor carrying a current in same direction, they will experience a force of attraction, This is important line and this is important line. All right, so please do not get confused about the thing that we have learned over here. So I have taken a case where the conductor is where the current is coming outward. You can cross verify by making or by taking the current outward or away from you. All right, and in that case also you will going to have the force of attraction. All right, let us move to the case where we are having the current in opposite direction. All right, so please wait, let me draw it. Okay, so here let me take for this, the current will be dot, which is having the current I1, and here let us reverse. This time I will take here cross, which is having the current I2. Now this dot will going to give the magnetic field. See, this is outward, curl the finger, it will going to give the magnetic field in anti-clockwise direction. Similarly for this I2, just a second, let me draw it. Okay. See, for this it is anti-clockwise, like this it will be, and for this I2 the magnetic field is what? Inside the board, so it will be clockwise. So this will give the magnetic, this is the magnetic field due to current I2, so B2, and this was due to I1 current, so this will be B1 and B1. All right, now let us find the force here. Now F1, 2. So force of 1 on a conductor 2. So this is conductor 1 and conductor 2. So we will have to take the current element here, I2 del L2 into and the magnetic field of first, which is B1. All right, this is vector. So this is equal to I2 del L2, and what is the direction of the current element of this conductor? Since this is moving in inside, na, so this will be minus AX into B1. What is the direction of the magnetic field of B1? It is upward, na, so it will be AZ cap. So this will give you I2 del L2. B1 is mu naught H1 upon, mu naught H1, or let me replace H1 with I1 upon 4 pi A. This we have seen. What is A? A is the distance between these two conductors. This is A. And what is direction? AX cross AZ vector. So what is AX cross AZ? AX cross AZ is minus AY. Okay, this is minus sign here. We have minus sign here. So minus AX cross AZ will be what? AY. So this will be I2 del L2 mu naught I1 upon 4 pi A. So this will be AY. Yeah. So the force here, will be in AY direction like this. This will be F1, 2. Force of, the magnetic field of 1 will give the force on X2, on conductor 2. So this will be the in AY direction. Now let us find for F21. F21. So you will have to take the current element of the first conductor del L1 into magnetic field of second, which is B2. All right. So this will become I1 del L1. And what is the direction here? It is outward. So AX cap into B2. And what is the direction of B2? B2 is in direction upward. So AZ. So this will give the value as, replace B2 with mu naught I1 or mu naught H, you can say. So mu naught I2 upon 4 pi A. So I1 del L1, this is mu naught I2 upon 4 pi A, and this AX cross AZ vector. So this becomes I1 I2 mu naught, let me take mu naught here, mu naught I1 I2 upon 4 pi A into del L1, and this will be minus AY. All right, so minus AY means this is in this direction, the force here. The force here will be in opposite direction. See, like this. So this is F21. Now it is very clear that whenever a current carrying conductor are in opposite direction, then the force between these two will act in the opposite direction, or the force will be as a kind of repulsion. So therefore, whenever a current whenever a current carrying conductor are having, sorry, whenever a conductor or whenever a two conductor carrying a current in opposite direction, then they will experience a force of repulsion. Very important line. Okay, opposite direction. Why this is important? Because in the transformer we have a limbs, and in that limbs we are placing the winding. So whenever we have a malfunction in the transformer or inside the transformer, the windings may get displaced, and this is only due to the force of attraction or repulsion. So there are vast chances of getting the malfunction of the transformer or in the transformer, and we should do not get it happen, otherwise it will going to damage the transformer. So there are certain kind of remedies in which we can remove all those all those demerits. Anyway, this is not the part of dictation over here. So this we have taken care in the our online or offline classes. So once you're going to enroll, definitely you will come to know that what are the disadvantages of the of this and how we will going to rectify all those. All right, so let us move ahead with the next part, which is basically a practice problem over here. Okay, so this is the one problem which I kept here. See, determine the magnitude of force and its direction. Assume B is 0.25 Weber, current from top to bottom, and the length of conductor is 1. This is a conductor and the conductor length is 1 meter, and the magnetic field B is what? It is outward. It is outward. So first we need to find the magnitude, and after that we need to find the direction. So we are provided with the force then F is equal to I L into B. DL is what? Small length or the some portion of the conductor. So here the total conductor length is given. So I have replaced the del L with complete length. What is the current here that is given? Current here is 5 ampere, which is top to bottom. So what is the direction then here? Direction here is top to bottom, which is minus AZ, isn't it? Okay, let me replace here. 5 ampere into L is 1 meter into magnetic field is 0.25. Now, what is the direction of the length of conductor? It is downward, not top to bottom, means minus AZ cap into what is magnetic field direction? Magnetic field is coming outward, so it is in plus AX direction. So this is equal to, this is 1 by 4, 5, 1.25 is, please check, this is 1.25 Newton. And AZ cross AX will be what? AZ cross X is AY, and due to this negative sign, it becomes minus AY. Cap. All right. So the magnitude of force is 1.25 Newton, whereas direction of force is is towards left. Done. You can also use the Fleming left hand rule to find the direction. All right. So the question is very simple. This kind of question you can find in your academic exam. Anyway, when we had a conventional type of paper in the GATE, so in that such kind of question was usually asked, but currently since we have only the MCQ NAT type of question, and so we cannot expect such kind of question in the machine. All right. So let us move ahead with the next part, which is statically induced EMF. So this we have seen in the last lecture that the statically induced EMF will going to have the EMF of such kind that if the conductor is not moving. So in this we have seen the Faraday's laws, and from there we determine the EMF equation. So let me write it directly. So here EMF E is basically what? D psi by dt. What is psi? Psi is the flux linkage, and this psi is equal to what? N phi. N is number of turns of the coil, and phi is the magnetic flux. So this N is constant. Let me take out of the derivative. So this will become N d by dt of phi. Okay, this is phi symbol. So this is the EMF equation. Done. All right. Now in the transformer, basically in general term, this flux is basically what? Magnetic field density into area, where phi is magnetic field density into area. Let us replace here. So this will be equal to N d by dt B into A. Since conductor is not moving or the conductor is static, this means that area of the of such type of machine will not going to change. So this area will be constant. So let me take out of the derivative. So this will become N into A dt B. So this is known as the statically induced EMF. All right, this is known as statically induced EMF. All right, so please do remember either this one or that one. All right, either that one or this one. Done. So let us move to the next part, which is a question over here. Determine the induced voltage at the terminal AB for the given circuit, where phi, which is magnetic flux, equal to 10 sine 314 t milliweber, and number of turns N equal to 100. So this is terminal AB, and we need to determine the voltage here at terminal A and B. Then A and B, and this N is number of turns, here is given as 100, I guess. Yeah, 100. Now see, this is a transformer, and in that we have a 2 winding, and this flux is moving in this direction. So here we need to find the induced voltage. So in the last lecture we have seen that the effect means from the Lenz's law, effect opposes the cause. So here the EMF will going to be induced in such a way that it will going to oppose this flux. In this winding, what is the flux direction? From downward to upward, from down to top, Then the induced, then the induced current or the flux has to be what? The induced flux has to be in this direction, such that it will going to oppose. Let me use different color. Okay. This is what? This is phi induced. So main flux is moving upward, then phi induced means the effect opposes its cause will be in downward. So this flux will generate the EMF, but direction will be given by the Lenz's law. So here E will be equal to, n d phi by dt. N is given to me, which is 100 into d by dt. What is phi? 10 sine 314t into milliweber, so 10 to the power minus 3. So this becomes 100 into 10 into 10 to the power minus 3 into derivative of sine will be cos 314t into derivative of this, we will get 314. So this becomes 1000 10 to the power minus 3 will be 1. So 314 cos 314 t volt. But this is what? This is the magnitude. Then what will be the polarity? Polarity will be given by the Lenz's law. Now see, what will be the current in this winding such that we will have phi induced in this direction. So it will going to be given by Fleming right hand palm rule. So see, point your thumb in the direction of phi induced, which is downward, isn't it? Then this forefinger will give the direction of induced current. So the induced current from back side, it will be towards right, and from front side it will be towards left. So from the front side it will be towards left like this. From back side it will be towards right. So direction will be this one. So in the yesterday class, I told you how you are going to determine whether A is positive or negative. Just connect the fictitious resistance here at the terminal AB, fictitious resistance like this, R. So this current I induced will enter into the R. So this makes this point as plus and this point as minus. So A is positive and B is negative. So basically here EAB. So this implies, let me write here, so this implies EAB, where A is positive terminal and B is negative terminal, this is equal to 314 cos 314 t volt. Alright, so in this way you will going to learn the transformer, and which is the basics. Alright, just you need to use the Faraday's laws and the Lenz's law. Alright, so let us come to the dynamically induced EMF or the motional EMF. So in the motional EMF, what we need to do? Just a second. Alright, so in the motional EMF, we require a conductor such that an EMF will going to be induced in that. So let me draw the conductor here. Okay, so this is the conductor we are having, all right. Now let me take the conductor is moving in this direction. Your conductor is moving in this direction V. Now this conductor is what? It will going to have the electron such that it will going to it will going to have a current, and due to that it will going to have an EMF in that, isn't it? Let me make it more clear. We have a conductor, and this conductor is what? Under the effect of magnetic field. So here magnetic field is what? Inside the board, and this conductor is moving. This conductor is moving. So definitely it will going to experience a force, and that will be given by F equal to, just a second, F equal to Q, which is the charge, V velocity of the conductor into magnetic field. All right. Now here V is what? Velocity of the conductor. Now here velocity is in which direction? Is in y direction, isn't it? So this Q V A x cap cross this magnetic field is inside. So the direction will be minus AX. So B times minus AX. So this gives the force as, just a second, this gives the force as Q V B, and AX, sorry, this is inside na, okay, and this is AY, extremely sorry, this is AY, not AX, this is AY. So AY cross minus AX, this is AY cross minus AX. So AY cross minus AX will be what? This will be AZ, Q V B AZ. Done. Now this Q is the charge. Now if Q is positive, means the force due to positive charge. Let me take F plus. F plus means force due to positive charge. So this will be equal to Q V B, which is in AZ direction, A cap basically. Okay, this is cap. Done. And the force due to negative charge. So since Q is negative, can I write this is minus, sorry, Q V B here as minus AZ. I have taken this negative sign inside to this. So here the force due to positive charge under the presence of magnetic field will be where? In upward direction, isn't it? In AZ means upward. So what this magnetic field do? It will tends the positive charge to accumulate at the top, which is in AZ direction. Similarly, the negative charge will going to be accumulate in the minus AZ direction, which is downward. Compare it with XYZ axis. So plus charge will be here and negative charge will accumulate here like this, and plus charge will be here. All right. Now this plus charge and negative charge, what it will do? This plus charge and negative charge, what it will do? It will going to generate an electric field. So whenever we have a positive charge and negative charge, then it will going to generate a electric field. So we have a plus charge here, negative charge here, and the direction of electric field is always from positive to negative charge. It is the basics of your electromagnetic theory. All right, so this is the EMF, sorry, the electric field, not EMF. This is the electric field, E. Done? Any doubt? Now, one more thing that we are going to have, this electric field going to have, let me change the color just a second. Now, this electric field will going to give again a force. Why, sir? We have seen na, in Lorentz law equation, the force is basically what? QE plus V cross B dot Q. So force due to magnetic field is here. Then the force due to electric field will be what? Since we have an electric field here, so again we are going to have the electric field force. So it will be given by equation like this. Force due to electric field. So F positive will be what? QE. I have taken the force of positive charge under the presence of magnetic field. Since Q is positive, then F will be in the same direction as that of E. So here the force due to electric field for the positive charge will be in the same direction as that of electric field. So it will be like this. Wait. Please let me know which color is visible. I hope. Okay, let me make it yellow one. So this is the force due to the presence of electric field, okay, on the positive charge. Now what about negative charge? The F negative, F negative will give the force in opposite direction. So that will be upward. Am I clear? So this is in downward direction and this is in upward direction. Now see the thing, what is happening to the charges under the presence of magnetic field and electric field. The positive charge is accumulated upward due to magnetic field, whereas this electric field makes this positive charge to move in the downward direction. See, in downward direction due to electric field, whereas the magnetic field makes the positive charge to be accumulated in the upward direction. So these two are what? Are in opposite. These two are in opposite. So under the equilibrium condition, just a second. Under the equilibrium condition, magnetic field tend to move in upward, electric field tend to move downward. So the net effect of the force will be what? Net force on a charge will be equal to 0, isn't it? Will be equal to 0. So this F is basically due to magnetic field plus due to electric field, which is equal to 0. So can I write your Fe is equal to minus Fb. What is Fe? Fe is what? Q times E, whereas Fb is what? V cross B Q. So this implies your electric field, QQ will be cancelled out. Your electric field is equal to minus V cross B. This is vector basically. This whole thing are vector. What is V here? Voltage? No, that is current. Okay. That is velocity of the conductor. So this equation is very important. All right. So we have got the electric field equation, but my interest is not the electric field. My interest is to find the EMF. So the EMF under the presence of electric field is given by V equal to minus integral E dot dl. E is the electric field, dl is the length of the conductor which is placed in the magnetic field, in the magnetic field. So minus integration. This is the equation that you will going to get from the electromagnetic field theory. All right. So this is voltage. Note the velocity. This is voltage equation. Okay. So this is voltage. E we have got as minus V cross B, minus V vector cross B vector dot dl. So this minus minus will become plus. We will get integral V vector B vector dot dl. So this is the voltage equation, induced voltage equation in the conductor. All right. So see. Okay, one more thing. What will be the polarity in this case? Means what will be the polarity of the voltage in this case? Whether the downside will be positive or the upside will be positive. Now in the diagram it is very clear that we have used a concept. In that we will going to, from that we have found that the positive charge will be accumulated in the upward direction. All right, in the upward direction. But here dl is what? Here dl is what? dl is always here. Let me write here. dl is directed from negative charge to positive charge. All right, it is direct, means the dl means if you want to integrate, the lower limit will be what? Of the length where the negative charge is accumulated, and the upper limit will be what? The length where we have a positive charge as as an accumulation. All right. So this will be the dl direction. Now in this case, negative charge is here and positive charge is here. So we can imply or we can give the symbol for for the EMF like this. And in most of the book you have seen such kind of symbol for the battery for the EMF. Or whereas this arrow is always pointing from negative charge towards the positive charge. So negative charge is here, positive charge is here. So this is the convention that is followed by the IIT faculty or most of the standard books. All right. So if in future if you are able to see such symbol for the EMF, this means that arrow give you the positive terminal, and this tail will give you the negative terminal. All right. So in this two way we can represent the battery polarity. All right. So let me mark here. Suppose this is one representation of the battery polarity, and this is equal to what? Basically this is equal to negative charge will accumulate at the tail, so minus, and positive charge will accumulate at the head, so this will be plus. So minus and plus, like this. So we can represent in two manner our EMF. Done. So in this way we will going to find the motional EMF or dynamically induced EMF. So I hope all things are clear over here. In case of any doubt, please do reply in the chat box. Whenever I get free, I will try to reply with the same. All right. This is E basically. Now let us come to the next part, which is dot convention. Which is dot convention. Now what do you mean by dot convention? See, the dot convention is used to find the polarity of the EMF in the mutual winding. In the mutual winding. So what do you mean by this? Suppose you have an iron core. This is an iron piece. Okay, assume this is an iron. Okay, in that iron we have two windings like this. This is one winding which is having two terminal, which is named as A and B. And we have another winding like this, which is having the terminal named as X and Y. Now here in the first winding, means these two are not connected. Now please make it clear, these two are not connected. In the first winding we are going to have an electric current. We are going to have an electric current like this. Okay. Now since we have an electric current, definitely it will going to give the magnetic field. Then what will be the direction of magnetic field in this case? See, this is the iron and this is the front part of the winding. So the magnetic flux direction will be from right to left, means in this direction. this is the flux direction phi due to this coil, due to current in this coil. Now we have to mark here one dot, means for such type of concept, wherever we need to place a dot in the secondary coil or in the mutual coil, then in such cases, in the one winding where the current is given to us, we will be provided with a dot symbol. Dot symbol gives you the information that in that winding the current is entering in which of the portion. So here, since the current is entering here, so we will provide a dot. Or suppose if the direction is not given to us, then this dot simply implies that the current is entering from here. Done? Any doubt in this? Now in the next coil, this flux will also coming from here, isn't it? This is what? This is iron bar, and magnetic flux is always flow in the closed path. So this magnetic flux will go into air and it will back like this, and it will again going to enter into this flux, into this iron bar. Now here the EMF will going to be induced in such a direction that it will going to oppose the what? The cause, means effect opposes the cause. So here the EMF will going to be induced by this flux, but the current here will be in such a direction that it will going to oppose this flux. So since the flux is in this direction, then to oppose this flux, here the flux will be directed in will have to be directed in this direction. Okay, so this is phi induced. Phi induced. Done. Now to make this phi induction in this direction, what will be the current direction in this coil? Again using Fleming right hand palm rule. So flux is in this direction, then this forefinger will curve in the direction of induced current. So from the back side it will be upward, and from front side it will be downward. From front side it will be downward. Okay, so it will be like this. See, from back side it will be upward, from front side it will be downward. So from back side it will be upward, from front side it will be downward. Again, whether x is positive or y is positive, we will going to use the fictitious resistance. So connect a fictitious resistance here like this, R. So this current, if it flows through R, it becomes positive and this becomes negative. So here X will be the positive terminal and Y will be the negative terminal. So in this way you will going to find the EMF due to this mutual flux, and this concept we will going to use n number of times in our transformer. Done? Let me make one more question over here. This is iron bar. Okay, please do not assume anything else. Okay. this is X, this is Y, and let me take okay, one more thing I think we have forgot. Yeah, one more thing, extremely sorry for that. I have forgot that thing. Now here we need to mark a dot. Here we need to mark a dot. So here the dot will be placed, means the current which is given by the source will have the dot at the terminal where the current is entering. But in the mutually coil or in the mutual coil, we need to place a dot in that terminal where the current is leaving. So the current is leaving here. So we will mark a dot where the current is leaving in the second coil. Done. So this is basically what? In this way we will going to find the EMF, magnitude of EMF and the dot placement. So it is clear that in the first coil where we have a voltage source and the current is entering, we will put a dot, and in the second we will place a dot where the current is leaving. Let me back to the question, just a second. All right, so let me complete the figure here. This is P terminal and this is Q terminal. Okay, so the question is determine whether a terminal P is positive or negative. Positive or negative. So please do solve and reply the answer in the chat box. All right. So with this we have completed the lecture number 5. All right, with this we have completed the lecture number 5, and in tomorrow's session we will going to start the lecture number 6, and definitely we will going to see a lot of things in the electrical machine. And my dear friend, we have a lot of things to cover. All right, so this is only a beginning, and we have completed only 20 to 30% of the basics of the electrical machine, and from now onward we will going to study a lot of things which is one of the essential requirement for the transformer and the synchronous induction and DC machine. Alright guys, so if you have liked the session or if you have enjoyed the session, please do hit the like button, and also share the session link with your friend, and do subscribe our YouTube channel. Alright, and also press the bell icon so that whenever we are coming up live or with the new initiative, you will instantly going to be get notified. Alright, so bye bye and take a very good care of your health.